In this lecture, we're going to discuss how to determine the empirical formula of a compound. Empirical formula is defined as the simplest whole number ratio of the elements in a compound. It may or may not be the actual molecular formula of the compound, but it is always just the simplest whole number ratio of its elements to each other. And it comes about because the molar ratio of the elements in a compound is what determines its empirical formula. So literally, that's all it is. It's a molar ratio of the elements in a compound. And you can figure out what the empirical formula of a compound is from its mass percent composition. Mass percent composition can be determined experimentally using equipment such as an elemental analyzer. So let's do some examples where we see how to figure out the empirical formula of a compound. Let's take an example where we have a compound that contains only potassium and oxygen, and it's 82.98% potassium and 17.02% oxygen by mass. Using that information, we can predict its empirical formula. So what you need to do whenever you're given mass percent composition is you need to figure out the molar ratio. So that's the key to solving all of these problems. You want to figure out the mole ratio of K to O or O to K, either way. And the best way to do this, the easiest, simplest way, if you're given the mass percents, is to assume that you have 100 grams of the compound. Assume you have 100 grams of the compound, because if you have 100 grams, then you know that 82.98 of those grams are going to be potassium, and 17.02 of those grams are going to be oxygen. So if you have percentages, assuming 100 grams simplifies the calculation considerably. So in that 100 grams you have of this mysterious potassium and oxygen containing compound, you are going to have 82.98 grams of potassium and 17.02 grams of oxygen. Now, all you need to do is look up in the periodic table to find the atomic masses of potassium and oxygen to the number of moles of each of these elements. So let's try to do that. Potassium in the periodic table, we can find its atomic mass, and we can see that we have 39.10 grams of potassium per mole. That's just the atomic mass of potassium. So 82.98 divided by 39.1 is 2.12 moles of potassium. So you see what we did here? We're canceling out the grams, so we're left with moles of potassium. For oxygen, looking at the periodic table, we have 16 grams per mole. So 16 grams of oxygen per mole. That's just the reciprocal of the atomic mass of oxygen. We can cross out the grams, and we take 17.02 divided by 16 to give us 1.06 moles of oxygen. So now we have the molar ratio. We have 2.12 moles of potassium for every 1.06 moles of oxygen. So mathematically, the easiest way to break this down is to divide through. So divide both of these numbers by the smallest number to get the ratio in whole numbers. So if we want the molar ratio of potassium to oxygen, that's 2.12 moles to 1.06 moles. If I take 2.12 and divide it by 1.06, that's 2. So that is going to be a 2 to 1 ratio. And that gives me the empirical formula of K2O. So this is the answer that we are looking for, the empirical formula of K2O. What this is telling me is that I have twice the number of moles of potassium as I have oxygen in the formula. So that's giving me the K2O molar ratio. So this is an empirical formula. It is not necessarily the molecular formula of the compound. It's just the smallest whole number ratio, and that is the definition of an empirical formula. Let's do another example now. Let's say we have a compound and we have determined that it has 40.9% carbon, 4.58% hydrogen, and 54.5% oxygen by mass. Can we use that mass percent composition to figure out its empirical formula? So let's take the same strategy that we took before for the previous example. We want to assume that we have 100 grams of that compound. And if we have 100 grams of that compound, then we can use those mass percentages to figure out the number of grams of each element. So assume that you have 100 of the compound. In that 100 grams of the compound, you have 40.9 grams of carbon, 4.58 grams of hydrogen, and 54.5 grams of oxygen. Now, using the periodic table, I want to look up the molar masses of each of these atoms. So for carbon, I'm going to take its molar mass. It's 12 grams per mole. For hydrogen, it's 1.01 grams per mole. And again, I'm using the reciprocals because I want to cancel out the grams and be left with the moles of each element. Oxygen is 16 grams per mole. So in each of these instances, I am able to calculate the number of moles of each element, moles of carbon, moles of hydrogen, and moles of oxygen. 40.9 divided by 12.01 gives me 3.41 moles of carbon. I have 4.53 moles of hydrogen and 3.41 moles of oxygen. So then we want to take the same mathematical approach. We want to transform this into a whole number ratio, which often you can do by inspection. But the safe thing to do is to divide every number. So divide every number by the smallest number. So I would take the 3.41 and divide every number by the smallest number. And that's going to give you a ratio of C to H to O. Let's see, we have 3.41 to 4.53 to 3.41. And if I divide all of those numbers by 3.41, the ratio becomes 1 to 1.33333, 1.33 repeating, to 1. Now, you want to transform this into a whole number ratio. So you want to multiply through by a common factor. And since you have a third here, the common factor here is going to be 3 in this case. So you want to multiply through all of the numbers by 3. And that is going to give you a C to H to O ratio of 3 to 4 to 3. And that means that the empirical formula is C3H4O3. This is going to be the empirical formula of that compound. It's the simplest whole number ratio of elements in that compound.